Okay, well, I think we can start then. So I'd like to welcome everyone to the Quantum Matter seminar. We're really happy today to have Rahul from the physics department, and he's going to tell us a bit about the landscape of tensor network states preparable for measurement. If anybody has any questions over Zoom, please unmute and just ask. And please join me in welcoming.
Yeah, thank you guys so much. Thanks so much for the opportunity to speak. I'm super excited to tell you guys today about a series of 2 papers that I recently put out with a really wonderful collaborator and friend, Ruben Verresen, which broadly center around trying to understand which quantum states can you create using measurement, but with sort of the added flavor of trying to understand, kind of fundamental properties of measurement as a tool for creating entanglement and correlations. And I should say that at the same time or slightly after we posted these papers, there was actually a couple of parallel works that kind of address similar questions to that we do. And what's nice is that, of course, our results agree where they overlap. But I think all of the papers, come at the problem with complementary perspectives. So if you're interested in what I have to say today, I guess make sure to check out the other papers as well. So with that, maybe the best way to kind of motivate my talk is by saying that we know of a lot of very interesting emergent phenomena that can occur from, entanglement in the many-body ground states. So in particular, it's already surprising that, entanglement in ground state wave functions can lead to kind of rich quantitative behaviors such as correlations and collective fluctuations, even in the absence of any temperature being present in a many-body system. But it can also, entanglement in the ground state can lead to kind of exotic qualitatively distinct behaviors, and is closely related to the notion of a phase of matter. And tied with that, comes the emergence of new laws of physics that occur at low energy, including new types of particles, things like anyons, Goldstone modes, things like this. And so the basic problem that I'm going to be talking about today is that while we know of a lot of very interesting, states of matter that can occur, we don't really have a systematic understanding of how to realize them in the lab. So this is a problem I've been thinking about a lot in my PhD generally, but one kind of observation about this is that it's sort of fundamentally context dependent. Like what do I specifically mean by the lab? And in part that's inspired by new experimental opportunities. So for example, the recent advent of highly tunable synthetic quantum materials such as Moiré systems or cold atom quantum devices. And in the context of these new technological developments, the question has a sort of practical flavor to it, which is that we want to kind of understand the power of quantum devices. So specifically, given some experimental capabilities that I have available to me, what entanglement patterns can I explore in my device? But I want to sort of emphasize that despite the fact that this is a bit of a context-dependent question, I think it has a bit of a fundamental flavor to it if you kind of take a resource-theoretic lens on what states you can create. So in particular, understanding how to and how not to prepare a state, given some experimental capabilities, is often a good way to get an understanding of its properties. So case in point, long-range entanglement is really the backbone of topological order and even symmetry breaking. And it definitionally is the property that a state cannot be created using a finite depth local unitary circuit or equivalently finite time evolution, right, under a local Hamiltonian. So and just by knowing this fact about how you cannot prepare these long-range entangled states, you can get a lot of insight into the property of topological phases and symmetry breaking states. So for example, the error correcting properties of topological phase, for example, can often be understood from the context of it being long-range entangled. So given this, a kind of modern and salient experimental context is that of digital quantum devices. So, I'm sure everybody is familiar with some examples that you've heard in the news of these digital quantum devices, things like trapped ions or superconducting qubits, or more recently, neutral atom arrays. And these, digital quantum devices are so-called digital because they have 2 types of resources available to them. So the first is strictly local unitary gates. What I mean by that is that, the experimenter, of a digital quantum device can act on qubits, like some finite number of qubits with some unitary. So either a 2-qubit gate or a 3-qubit gate or something like this. But in addition to this, they also have the ability of performing local measurements of the system. So beyond just using measurements as sort of a readout tool, you can also, during the process of your quantum operation or something like this, you can have measurements kind of interspersed throughout the process. And you can also condition things that you do later on based on measurement outcomes.
So here when you say local unitary, so you mean local in space, not just But experimentally, why can't they just take 2 qubits and then just do something? than that?
Oh yeah, so it depends on architecture, right? So some architectures you can like spatially rearrange things, like Rydberg's and even some trapped ion processors. But in other architectures, like the qubits are literally fixed on a chip, right? Like so, yeah, there's a strict notion of locality, right, for the gates that you have. Yeah, good question. So we want to try to understand what types of states can you create given a finite amount of both of these resources, like a finite depth local unitary circuit and some finite number of measurements. And so, let's break it down. What's the power of finite depth unitaries in creating quantum states? So specifically, what properties do all of these states sort of share, right? So at the level of correlation functions, actually, you can already see that finite depth unitaries can only create kind of very unnatural correlations in some sense. So what I mean by that is that if you look at this unitary circuit, you'll see that it has a strictly finite light cone, which is to say that if you measure some 2-point function, right, at a distance that's larger than some number times the depth of the circuit, right, then beyond an appropriate distance, all correlation functions are exactly 0. That's very unnatural, like relative to kind of typical quantum states that you see in let's say materials, where you'll see exponentially decaying correlations and things like this. So, this already kind of highlights some restriction, right, that finite depth unitaries have, right? And I'll call states that have this property where, the correlations, kind of are exactly 0 beyond some point or reach their asymptotic value beyond a strict finite range, right? I'll call these fixed point states. It's a bit of a loaded term, but this is at least what I mean when I'm talking about fixed point states. And in addition, I kind of already mentioned that finite depth local unitaries can't create long-range entangled states, but it's kind of useful to take a phase of matter perspective on what I mean by this. So in particular, if your experiment starts off in the trivial phase in any way, then by acting with finite depth unitaries, if there's a GHZ phase or a Tor code phase anywhere putatively accessible within your system, unitaries really can't hop you between, can't help you cross these phase boundaries. So these are the sorts of 2 restrictions that you get when you consider unitaries. It's been recently appreciated that you can actually use measurement to prepare more interesting and more exotic types of states than you can with unitaries. And the idea is always sort of like teleportation. In particular, I'm sure all of you are familiar that by using measurements and classical communication, so some outcome conditioned unitary, right, you can teleport one end of the bell pair. So just to be explicit, if Alice has 3 qubits and Bob has 3 qubits, and Alice has a bell pair, on her own, and Bob has his own bell pair, and then they share one bell pair, they can perform measurements on their, qubits, and then Bob can perform an outcome conditioned unitary in order to create a longer bell pair between the 2 of them. So this is the way to get longer range entanglement by using measurement and feedback, or unitaries conditioned on those measurements. And by slightly generalizing the idea to the many-body setting, people have demonstrated that actually you can use measurement and feedback to be able to prepare, like the GHZ in finite time or the Tor code. And this is, not only quite theoretically enticing, like we can try to understand like hierarchies of, phases of matter and things like this with this additional resource, but it's also led to some really beautiful experimental results, such as the realization of a Tor code topological order and also non-abelian topological order. But I want to sort of emphasize that this is still quite a frontier. We don't have a really good understanding of what measurements, can do generally, right? They clearly don't interplay cleanly, as cleanly as unitaries with locality, right? But there's kind of a general question of what they can, what types of states can they create? So we know that if you start from the trivial phase, you can perform some set of measurements and feedback to create, kind of fixed point representatives of, say, the GHZ or the toric code. But again, these fixed point representatives are very unnatural, like from the perspective of ordinary quantum states that you encounter. So, they have these strictly finite correlations in some sense. So a natural question is, can you create, more generic types of correlation functions or more generic types of correlations and entanglement, right, using measurements and unitaries? So specifically, can you not only probe isolated points in a putative phase diagram, but also kind of go outwards from phase diagrams by using these 2 resources? A priori, you might be surprised if, the answer was yes, for a couple of reasons. So maybe the first reason is that the kind of smooth continuum behavior of an exponential decay seems kind of in tension with the idea of like a strictly local measurement or a strictly local gate. That's one reason maybe. And then the other thing is the fact that it needs to be deterministically preparable, means that no matter what the measurement outcome is, all of the states need to be related by some unitary, right? That can't increase the correlation length. So any measurement outcome needs to have the exact same correlation length in some sense, right? So, a priori, maybe this, is not natural to be true, but it turns out that in 2023, there were two really nice isolated examples where they demonstrated that you can actually create finite correlation length using measurements. And this kind of opens the game up a little bit. And we're motivated to ask the question, right? What more general patterns of entanglement and correlations can be deterministically created, right, from measurements and feedback? So, that's kind of the central question I'll be addressing today. But, just to kind of adjust the title a little bit, tensor networks appear in the title, and don't be scared if you don't know what a tensor network is. If you don't know anything about tensor networks, that's fine. I think the talk should be understandable. But to kind of spell out their role, given the ingredients that I've listed for digital unitary circuits, turns out that every preparable state that you can create, given the ingredients I mentioned, local unitaries and measurements, is some subset of tensor network states. So that's really, like all there is in some sense, or like it's a strict superset of all that you can create. So the way to see that is maybe a few ways. So first, consider the circuit diagram of any digital quantum process, and I'll even allow you to post-select. So force the measurement outcome, right? This is of course unnatural, naturally, right, in experiments, but it's a strictly more powerful resource than having random measurement outcomes. And in this case, by just charitably kind of partitioning parts of the diagram, right? You can reshape this into something that looks more ordinarily like a tensor network. Even if you don't know what this picture means, it looks, by just picking your tensor appropriately, right? You can kind of get this thing to look like a tensor network. So as a result, we're kind of motivated to say that like tensor networks will be sort of the natural language for understanding what states will be preparable, right? And quantum devices, and these digital quantum devices. So with that in mind, I guess I'm going to break my talk down into two parts. So the first part will be to try to understand, kind of a little bit more phenomenological. So I'll just provide a specific protocol for creating a really large landscape of phases or quantum states using measurements. So specifically, not only will we get like isolated points in phase diagrams, but entire, landscapes of, things that look almost like phase diagrams, right? Where every point in the phase diagram is preparable using measurements, like deterministically. And this will extend to 1D examples and 2D examples. And these examples will be really quite interesting. And I'll show that this preparation protocol, I'll kind of isolate what's necessary and what was kind of circumstance in the preparation protocols that I used, right? And we'll understand rigorously, at least in 1D, kind of what types of states you can create, and this will really distill out the power of measurement. Just to kind of make sure that like the main physical point is not lost, throughout the entire talk. Kind of one cool thing that we can find physically, I think this is quite interesting, is that there's a kind of limit to the power of measurements, right, for creating interesting entanglement and correlations. In particular, measurement can either create interesting entanglement structure, right, in a way that I'll make precise, or it can create interesting structure of correlation functions inside of a state. But there's a kind of strict trade-off between the two. Like you can't have both. And I think beyond many body physics or condensed matter physics in some sense, right, I think this is a bit of a result on just understanding measurement as a quantum tool, some basic result in quantum mechanics. So yeah, something to look forward to. So maybe I'll start with the first part of the talk. So let's try to understand, how measurement can create, tunable families of states with a kind of budget example, namely, the GHZ state, but slightly away from its so-called fixed point. So specifically, I'm going to try to create, show you how to create this following state, which is e to the beta x acting on the GHZ state. So if you want to think about this, it's kind of like you're doing imaginary time evolution under the Hamiltonian, sum over all x, right? And I'm doing that on the GHZ state. So I've shown it graphically as well. So I've shown the GHZ as this blue, blob, and then like the little white circles are e to the beta x. Here. And just to kind of lay out its properties, right? It's a long-range entangled state in the same way that the GHZ is, and it also spontaneously breaks the Z2 symmetry. It's described by a chi-equals 2 matrix product state, which will be clear in just a bit, and it has a non-zero correlation length. So any non-trivial correlation function that you compute in the state, right, will decay exponentially. So let's try to understand how to prepare this systematically. So we'll start off with disentangled clusters, right, a product state. So specifically, I'm going to pick my clusters carefully, and I'm going to pick them to be 3-qubit GHZs, but with an e to the beta x acting, on the middle qubit of those 3-qubit GHZs. You might be wondering, okay, this seems kind of unnatural, right? How do you create e to the beta x acting on GHZs? But of course, it's a few qubit state, so you can just create it using unitaries. So if you start off with the 3-qubit GHZ, you can act with e to the I yz with the appropriate time evolution, right? And create these clusters. And now we're going to measure the clusters in the Bell basis. So what do I mean by Bell basis? Just the standard maximally mixed state on 2 qubits. So there are 4 of them. I'm going to suggestively label them by identity x, z, and zx. They kind of encode the matrix elements of the operators, right? That's kind of inside the ket. So for example, the identity has a 1 for both the 0, 0 entry and the 1, 1 entry, right? Whereas the x only has a 1 for the 0, 1 and 1, 0 entry. And this writing of the Bell states is convenient because you can always relate any of the Bell states to the identity Bell state by the action of, say, an X operator or the appropriate Pauli operator. And just to kind of convince yourself that measurements should be able to create the state, maybe plausibly, note that if all the measurement outcomes were identity, that's exponentially unlikely, of course, right? You would have prepared the GHZ perfectly with no need for feedback. So the way to see that is that the 3-qubit GHZ, is kind of a state that ties together the computational states of all 3 qubits. So they can all be 0 or all be 1, right? They're kind of all forced to be 0 or all forced to be 1. And then when I act with a identity projector, right, that ties the nearby qubits to be in the same computational state. So you'll get in this case, and the e to the beta x is sort of a spectator. So the point is that if you ended up getting this exponentially unlikely outcome, you would have perfect prep of the deformed GHZ state. But of course, we have to deal with errors in life. So let's consider a generic measurement outcome where you'll have, say, you measure the wrong Bell state, like the x or the z. So I'll call these kind of undesired measurement outcomes errors for reasons that are sort of clear. And we want to understand how do we correct these errors using unitary feedback. So we're going to use our favorite property of these Bell states, which is that I can pull out Paulis. And what's going to happen is that I can pull out a Pauli x from this x Bell state, and then I'm going to use the fact that xxx acting on the GHZ state stabilizes it. Like the GHZ is 0, 0, 0 plus 1, 1, 1. So if you act with all x, right, you return back to yourself. So that means that acting x on one of the qubits is the same thing as acting x on the other 2 qubits, right? So concretely, what that means is that I can shuttle this x acting on one of the qubits, and I can move it over to x acting on the other 2 qubits, and it commutes through the e to the beta x, right? So maybe just to repeat, we pulled out an x from the x Bell state, and then we moved it over one site by using this special stabilizer property of the GHZ, right? And then you could just iterate this process, right? But you can see that I pulled out a physical x on the physical level. So if I wanted to correct the system, I would just move the error over by a single x, right? And then I keep doing that, again and again. You can play the same games with the z, right? So you can pull out the z as we did before, and then use the fact that z acting on any of the qubits is yields the same state. So you can now shuttle the z over by 2 qubits, and restore it on the other site without ever touching the physical leg, right? This e to the beta x leg, and then just iterate again. So just to kind of summarize, if you have an x error, if you encounter an x error, how you can get rid of it is you can just act with a non-local x string, to the appropriate side of the x error, right? And similarly, if you have a z error, you just act with a z on the endpoint of your chain. So both of these are kind of highly non-local operations, right? But nevertheless, right, they occur in depth 1. They don't increase the entanglement of the state in any way, right? So yeah. So at this point, right, we've seen how to create. I hopefully have convinced you that you can create, the deformed GHZ state. But let's try to understand this in a more tensor networky language. Not to use tensor networks, but just to because it'll help us with like kind of dexterity of thought on how to create these states. So we can reinterpret that whole thing that I did as a tensor network, in a tensor network picture. And if you're ever confused about the tensor networks, you can always kind of fall back on this cluster picture that I gave you. So in particular, in tensor networks, we like to reshape things. So like these 3-qubit GHZ states, I can think about now as instead of being a 3-qubit vector, right, in an 8-dimensional vector space, right? You can think about it instead as a tensor, right, that has 3 legs or 3, like indices, each of dimension 2. And in the case of the deformed GHZ, the tensor looks something like this, where this T junction is just the Kronecker delta. So the Kronecker delta encodes the fact that I'm tying together the zeros, all the 0 states and all the 1 states, right? And then I have an e to the beta x, of course, acting on one of the legs. I can similarly reshape the measurements, right? So in particular, just the, this is a bit harder to digest, but the broad projector of the measurement is just another state, right? So you can draw it as with 2 physical legs, and there's this classical random variable, which is the measurement outcome, right? The measurement outcome can be any of the Bell states. And you can reshape that to something that looks more like a tensor. So just to be concrete, something like the identity Bell state, you just reshape, and in more matrix language, right? It becomes the identity operator. And similarly, I mean, the same thing is true for all of the other Paulis, Pauli Bell states. They just become the Pauli operators, right? And similarly, things like the orthogonality, the orthonormality of the measurement basis just becomes the trace orthonormality of the measurement basis. So actually, operators that have this sort of trace orthonormality property are called error bases. It's this concept introduced by Nil in 1996 for understanding error correction. So yeah, in any case, so as a result, you can take your digital circuit that looks like this and just reshape it into something that looks like a matrix product state, right? All the states become tensors, all the measurements become tensors, and these alpha, beta, and gamma that appear here are just random variables encoding the fact that the measurement outcomes are random. And so you can kind of see that measurements are kind of gluing together the MPS tensors, right? Like they're acting as like or maybe stitching or whatever word you like, but we'll use glue. And now we just need to understand how correctability works in this sort of language, right? But maybe you recall that in the deformed GHZ case, I was able to shuttle the X's through the tensors, or through the clusters, and shuttle the Z's through the clusters. That's kind of encoded in these rules, these push-through rules for how a complete basis of operators pushes through the tensor. Those push-through rules will just be the push-through rules that we kind of demand are necessary, right, in order to prepare something. So in other words, just to summarize, if your goal is to prepare a many-body state, I've drawn it as some higher dimensional object, but you can just, if the picture doesn't make sense, just think it's some many-body state. What you do is you prepare some set of disentangled clusters, A. You use measurements to kind of glue the clusters together. And then, the hope is that the measurement outcomes, right, can be corrected at the physical level, right? And that occurs by, having some condition on the tensors, which is that the measurement operators, the operators associated with the measurement outcomes, push through the network to physical unitaries that you can then correct, And I should mention that this protocol is kind of nicely, inspired by and generalizes the AKLT preparation protocol, which was one of the isolated examples, of a finite correlation length state that I was telling you about earlier. So, okay, now that we know the game, right, you can, it's very easy to cook up families of preparable states, right? You can just try to cook up tensors that you like, right, that should be gluable in principle, right? So just as an example, let's take the following tensor. So the tensor consists of, 2 so-called virtual legs, which is the left and right, legs that I've drawn here, and a physical leg that's a qubit of dimension 4. So, in the cluster language that I was talking about earlier, it's kind of like you have a state on 2 qubits, and 1 qubit of dimension 4. And basically, what this equation is telling you is that depending on the state of the depending on the state of the qubit, the 2 qubits that are part of the cluster, right, form one of the Bell states, right? Either sigma x, sigma y, sigma z, or the identity. And the probability of seeing those things, conditioned on what the physical leg is encoded by this lambda object, right? So just as an aside, the lambdas can be chosen to be real and non-negative and summed to 1 by normalization. It's just some technical point. And you can see that this is gluable, or it satisfies these push-through rules. Because if I try to stick any of the Paulis, like X, Y, Z or identity, right, they commute up to a phase with the other Paulis. So that means that I'll just have to act with some diagonal unitary encoding the phases that I incur to move my my Pauli to the other side of the tensor effectively. So for example, if sigma x was the thing that appeared here, right, then the unitary you'd use is like 1, 1, minus 1, minus 1, right, in the basis 1 x, y, z. So. And the fun thing is that there are now 4 parameters, all the lambdas, and they sum to 1. So that means that there are 3 parameters in total. They're non-negative, so you can actually draw phase diagrams of states that that can all be prepared. So, and you'll see that this phase diagram has lots of kind of misrepresentatives in it. Like, so the AKLT state appears, which was, shown by Kevin earlier, the cluster state, the Niel states, the GHZ, and even our favorite family, which is this e to the beta x, this deformed GHZ state appears as kind of the, wire, like the axes on the phase diagram. The entire interior is, forms a Z2 cross Z2 SPT. The wireframes are all long-range entangled. So it has a lot of interesting structure. And I think the key here is that, all of these things have tunable correlation links. So, like basically every point in the interior, except for, some fine-tuned points, has a finite correlation link. And not only that, actually, you have such an understanding coming from, this kind of structure that you can build your own correlation links. So you can just ask, how fast do you want certain operators to decay and how fast do you want other operators to decay? And, you can use this kind of formalism to just cook up states that have those properties. Yeah, it's quite fun. And, this doesn't just extend in one dimension. You can actually do this in higher dimensions as well. So in particular, it's possible to cook up higher dimensional examples. Here's just one example. So for example, you can kind of softly introduce the star projector of the toric code. So specifically, I'm imagining qubits living on the links of the square lattice, and I want to create the state e to the beta star, right, acting on the plus state. If you like, this is just a state that kind of interpolates between the trivial phase, right, which is the plus state, and when beta is infinity, I've imposed the toric code projector star, and that becomes the toric code. So it interpolates between the trivial phase and the toric code. Now, I'm not going to kind of go through the derivation, but you can see that there's some tensor network representation of the state. Specifically, the tensor, the tensors look like kind of similar to the deformed GHZ case, but now there are some extra circles, right? So there's atomards and e to the alpha z's appearing and stuff like this. And similar to the GHZ case, it satisfies some version of the push-through rules, right? So z's in this case push through from a virtual bond to the nearest physical bond, and x pushes through to the other side of a virtual bond, right? And there's a corresponding x at the physical level. So that's how you get kind of large families of tunable states, by just using this gluing procedure. But so far I've just introduced a specific protocol, right? It seems kind of arbitrary, right? Like, is there any sense in which this protocol is unique or specific or something of that nature? And another question is, there was a lot of things that seemed circumstantial, right? I used the clusters; they were associated with the tensors associated with the tensor network I was considering. But of course, the tensor network is not a unique representation, right? You can always have different representations of the same wave function. So like that's a natural question to ask. I also use the Bell states. Is that necessary? Like, could I use some other measurement basis? So what was circumstantial and what was necessary?
So can I ask one question?
Yeah.
So far we talk about preparing the states. You always work on open chain.
Yeah, right.
Is there obstructions on closed chain?
So on closed chains, so you can only deterministically prepare on open chains with the appropriate boundary conditions, but you can always probabilistically prepare with some non-vanishing probability on periodic boundary conditions. So in 1D, that's an example. Like there's some probability that as I shuttle my measurement error, they're all product to 1, let's say, right? And so there's some finite probability that you will be able to, so yeah, you only get deterministic preparation with a particular choice of boundary conditions, but otherwise it's probabilistic.
Yeah, and the things that you get from closed chains are sort of like different, like twisted boundary conditions.
That's right. Yeah, kind of.
But can you do it first on open chain? Then you say let's do it at a
probabilistically. So
it's always probabilistic.
Yeah, it'll also be probabilistic. Yeah. Good question.
We also have a question in the chat from Mike Friedman. He asks, can you make non-abelian phases this way, like the Fibonacci?
Yeah, you can. So something I didn't mention is like generalizations that we did to like further rounds of measurements. So actually this was kind of discussed in a previous paper. It turns out you can realize, large classes of non-abelian quantum doubles, twisted quantum doubles using measurements associated with so-called solvable groups. So those will have non-abelian anyons. So for example, D4 topological order has non-abelian anyons. I think if I recall correctly, Fibonacci is not preparable, but yeah, that's a good question. Anyways, so in trying to make this more rigorous and precise, we'll actually be able to isolate, in some sense, what is the power of measurements for creating entanglement and correlations, as I kind of alluded to. So specifically, just to make as sharp statements as possible, let's restrict ourselves to 1D. And I'm going to be a little bit more mathematical by having a definition. So specifically, we'll say that a quantum state is gluable if it can be deterministically prepared using the following ingredients. So, a product state of entangled clusters, first and foremost, something that looks like this. Some finite range measurements in a complete basis. So what I mean by complete basis is that any qubit that I measure, I completely measure out. So I'm not allowed to measure, say, just ZZ, which would not completely collapse my wave function. I have to measure ZZ and XX. That's an example. Like I have to measure all of the Bell states, not just some fraction of them, right? And then in addition, I'll consider, tensor product unitary feedback. That's as a technical point, less conditioned. So what I mean by that is, we were able to see that things swept to the right or swept to the left. This is actually a general feature of all examples that we found. It's unclear if it buys you anything to go beyond this. We've never found an example beyond this, but we take it as a kind of technical condition. And we then want to understand what the kind of space of gluable states are. Now, I should kind of emphasize that the reason that this definition is kind of natural is it kind of encodes the fact that measurement is really the only entangling operation in this procedure. The only thing creating many-body entanglement is the measurement step, right? Everything else is kind of few-body entanglement, right? Like between the clusters. And in that sense, right, understanding the space of gluable states, we kind of take as distilling the power of measurement in some sense, right? Like understanding what one round of measurement and unentangling, unitary feedback, can create. And I should say, by the way, like, when I said finite range measurements here, it seems kind of odd that I only pick nearest neighbor measurements. Like it seems like there are more general things in this framework. In the paper, we actually, we actually consider more general cursed measurement protocols, like things like this. But you can show by appropriately reordering and kind of restructuring your qubits locally that you can always kind of relate it back to the frame, the setup here. So you never have to consider anything beyond this. So, and as we also know, right, states that are created like this, we can just use our reshaping rules, right, to kind of say that they all have exact matrix product state descriptions. And from that, there's a natural set of questions that we can ask, right? Things that we asked before, like how are the clusters related to the MPS tensors of the target state, right? And in which gauge, right? Like these things aren't, there's no unique representation of a many-body wave function. So do you have to check all of them if you want to, check if something is preparable? And is there any condition on the measurement basis, right? Another thing is, given an MPS representation, how do I tell if the state is preparable? That's another natural question. And what does the space of gluable matrix product states look like? So we're going to answer these with a series of key theorems. So specifically, the first is a resource theorem, where to look effectively. So it tells you that every wave function that's gluable has a matrix product state description. But in addition, the clusters used for the preparation protocol have to be the matrix product state tensors in so-called canonical form. And that's quite surprising because you can take for any matrix product state, right? Of course, there's a gauge degree of freedom in the problem, but canonical form is a way to get rid of that. It's like gauge fixing that degree of freedom. And the only way to prepare, right, a matrix product state using this gluable, this framework of just local measurements and tensor product unitary feedback, right, is by using the MPS tensors in canonical form as your clusters. So that was not circumstance, it was necessary, right? The fact that I was using the tensors as my resource for creating the states. In addition, the measurement basis always has to be maximally entangled. So, I use the Bell states, but of course, if you're considering higher bond dimension or, higher entanglement states, you'll have to use some other maximally entangled basis. So just to kind of see this borne out, recall, as a reminder, right, the deformed GHZ has an exact MPS description. Its tensors were related to the cluster, and it's not very difficult to show that these, tensors are associated with, are the tensors in canonical form, actually. In addition, the measurement basis we used was maximally entangled. So all of these things are not circumstance, they're actually necessary. Any state that's preparable, will always share these sorts of features, at least under the ingredients that we listed. So this kind of heavily constrains where to look if you want to create, quantum states.
We have another question from Mike.
Yeah.
He asks, are preparable states non-universal in the B2B sense?
So at least the 1D states that we're talking about right here, can all be classically simulated. So depends on, what you want out of the state. But yeah, they can be, I believe they can be efficiently sampled. And I think, they're efficiently simulable, like you can compute properties from them. So, yeah, they're definitely not BQP complete. So yeah, it's a good question. Yeah, at least the rigorous theorems that we have are sort of in 1D. We have lots of examples in 2D. It would be interesting to see if, by using this, you can create things that are sort of, computationally complex. Yeah, but it's a very good question. In addition, those push-through rules that we saw earlier, right? I just sort of, required that the states I was creating had those push-through rules. Was that necessary? Was it circumstance? So it turns out that you can derive that actually any global state will have some version of the push-through rules. So in particular, a state is global if and only if there's a complete measurement basis, that pushes through the local tensors, right, to a set of operators that are also pushable. And this is a pretty powerful constraint on the MPS tensor. It actually completely allows you to classify the space of global MPS given a specific push-through pattern. So, you tell me a pattern of how you want the push-through rules to work, and you can classify all matrix product states that, are preparable via this thing called the commutant algebra. The point is, it's just some object that's computable, right? So if the notion of computed algebra is not so, familiar, it's just some object that's computable, given a measurement pattern. And finally, we now want to understand, right, what are the physical properties of these global states, right? I mentioned that they exist, right, and how to do them, and what, we've cooked up this resource theorem and this local tensor criteria. But we want to understand, what properties are required of states, right? And the broader physical point will end up being that the pattern of push-through rules, or how measurement errors are corrected, right, equivalently, right, is closely tied to the entanglement and correlation properties of the resulting state. So specifically, this was what will lead to this insight, of the trade-off between the preparable entanglement and preparable correlation functions. So specifically, just to kind of pick an example of a set of states that you could consider, let's consider what we call topologically global states. And they have the pattern of push-through rules that are sort of similar to the deformed GHZ case. So what I mean by that is that every measurement error that you can make has to be corrected by some non-local operation on the string. So you can see the X is corrected by a non-local string operator, and the Z is corrected at a location that's not anywhere localized to where you used it. So errors that are non-locally corrected, or have push-through rules that don't trivialize, we call topological errors. And if a complete basis pushes through to a complete basis in the push-through rules under this, we'll say it's topologically global. So this structure of the errors actually heavily constrains the states that you end up getting. So in particular, you can prove the following theorem, that if psi is topologically global, then its bipartite entanglement spectrum is constrained to be flat. And what I mean by that is that if you compute the half-chain, reduced density matrix of the system, and you compute its eigenvalues, there'll be 0 beyond some point because it's a matrix product state, but all the non-zero eigenvalues have the same, are the same. So yeah, and again, this is kind of a very unnatural, property, to encounter in normal materials or normal quantum states that you encounter. And it kind of highlights the fact that preparable states aren't generic in any sense. They have a lot of structure kind of owing to their preparability. And nevertheless, we've already shown that there's very large landscapes of these states. And in fact, all of these states are topologically global, and all of them, have flat entanglement spectrum. As an added aside, in some sense, for uniform push-through rules, effectively, this is all of the states that you can get, with one dimension 2. So it's not just a large family of states, it's all of the family of states. And, the fact that it's topologically global further constrains the order. In fact, any minimally entangled, symmetry-protected topological phase with an abelian on-site symmetry is automatically topologically global. So minimally entangled just means that the entanglement is consistent with the entanglement degeneracy associated with it being a symmetry-protected topological phase. And similarly, any short-range entangled abelian or any short-range entangled topologically global state with some appropriate condition on the measurement basis is forced to be an SBT. But the message I've kind of given, seems a little bit, maybe unsatisfying. Is the only types of states you can get things with flat entanglement spectrum. It's not such a big restriction, in the types of states. Also, it doesn't seem like you can get very much, more interesting in terms of entanglement structure. But to find more interesting types of entanglement structure, you just have to look at things that are not topologically movable. So an example is, e to the beta zz acting in the plus state. It's kind of like the opposite of this e to the beta x GHZ state in some sense, right? And just its properties are that it's a short-range entangled state in the trivial phase, and it's described by a pi+2 matrix Potter state with a non-flat entanglement spectrum. And its tensor is actually very simple. It's just instead of having e to the beta x at the physical level, you have e to the alpha x, where alpha is like parameterized by beta, just acting at the virtual level like this. So, your cluster is now, in terms of the clusters, there's an e to the beta x acting on, not the center, effectively. So, we already know that, the state has non-flat entanglement spectrum, but it can be prepared because it satisfies the appropriate push-through rules. So in particular, x pushes through to x at the physical level and x at the virtual level. And what that means is that, an x error, again, is corrected by a non-local string, but crucially, unlike the GHZ, a z error that you make has to be locally corrected. You can't move it through the e to the alpha x, that just doesn't commute, right? So we say, errors that are locally corrected are local errors, right? And we know that states that have local errors can have non-flat entanglement spectrum, which is in principle richer, in some sense more expressive, right, than things with flat entanglement spectrum. Expressive in the sense that you can get, a larger type, a larger class of, entanglement spectra available to you. But again, nothing like comes free. In particular, if psi is boolable and there exists a measurement error that is locally correctable, then it means that there must exist an operator that has zero correlation length, or is a fixed point operator in some sense. What I mean by that is that there will be some operator that exists that you can compute the correlation function of, and it will die exactly beyond some length scale. It will not have this exponential decay property. There may be other operators that do have exponential decays, but there will be at least one that has exactly zero correlation length. Like it doesn't, it dies exactly beyond some length scale. And so in some sense, if you want richer entanglement spectrum, you have to pay the price of being slightly closer to the fixed point in a sense that you can make precise, right? Like, so you can kind of capture this trade-off, right, with the no-go theorem, right? If you demand psi to have a rich entanglement spectrum, that is to say non-flat, and you demand that there are no zero correlation length operators, you want to be far away from the fixed point, then your state is not boolable. It's not preparable with one round of measurements in some sense, right? Yeah, this is a pretty, powerful no-go theorem, and it says that you can create interesting entanglement structure or interesting correlations, but not at the same time. And yeah, I think this is a quite nice result, kind of showing, the power of measurements for creating entanglement and correlations in many-body systems. So with that, I guess I'll, have some conclusions. So in particular, I've demonstrated how and when measurements can create quantum states that are beyond the fixed point. So specifically, I showed that there was a large landscape of preparable states that you can create, by using this game of gluing and stuff like this. But in addition, in 1D, I was able to show rigorous theorems distilling the power of measurements, specifically with this trade-off and also with the resources necessary to actually create a quantum state. In some sense, the representation of the state itself, its structure, determines fully how to prepare it. And I think that kind of goes to a broader physical, point that we can make, which is that really there's a trade-off between two types of questions that you can ask. One is, what experimental resources or regimes are necessary to realize interesting, phenomena, in let's say quantum devices or in natural materials. And the other question is really a question of structure. What is the pattern of entanglement present in, typical exotic low energy, quantum states? And in some sense, understanding how to realize something is a good way to understand its structure a little bit better. We were able to refine things like the trivial phase, right? By understanding, like that there are certain parts of the trivial phase that are more complex from the perspective of, state preparation, right, than other parts of the trivial phase. And equivalently, understanding its structure, right, like its order, things like this, is a good way of understanding, how to and how not to create the state. So yeah, I guess with that, thank you guys for your attention. And yeah.
Well, thank you, Rahul, for the lovely talk. Do we have any questions in the room?
What's happening in like the